This class is about dependent motion, where the motion of one particle is completely dependent on the motion of another. So as an example here, let's look at a rope and pulley system. Now we have to start out by making an assumption that the rope is of fixed length, so it doesn't stretch at all. Now you started working problems like these in statics, where you looked for mechanical advantage. That is, if the crate weighed so many pounds, how many pounds does the person have to pull on it to be able to lift it? In dynamics, of course, we're going to be looking at speeds and accelerations. So if we pull down at a certain rate, how fast is that crate going to rise? So there's a trade-off between that force and velocity. So for a single rope, here's how we do it. First thing is we write an equation for the length of the rope. Now you notice those places that are in red. If I draw this displaced and undisplaced, those lengths are going to be unchanged. And so we define the other lengths, in this case defined L sub A from the top pulley down to the end of the rope. And you can see that position L sub B that's going to get shorter as we raise the crate. And once we've written that equation, we set the change in length equal to 0, because as we've said, the rope can't stretch, and then find the relationship between the non-zero changes, in this case the change in LA and LB. And that same relationship then will exist for velocities and accelerations. So in this particular case, you notice that there's one length LA, there's two lengths LB, plus the red part, which we're just calling L prime. So when we do the change in length, of course, again, the L primes don't change, and we end up with this expression, which says that we have to pull down on the rope 2 feet for every 1 foot that the crate rises. And similarly, the relationships between velocities and acceleration would be the same thing. I have to pull down at twice the rate that the crate is rising. Again, if we look at that in statics, we looked at the same problem and said, okay, the force that it takes to lift the crate is 1/2 of the weight. So again, you see a trade-off. I'm getting lifting power, that is a 2-to-1 ratio in lifting power, but I trade off that in that I have to pull twice as fast as the crate rises. Now when you have multiple ropes, the procedure is similar, but it's a little different in that we like to measure everything, including the centers of the pulleys, from a common datum, that is the top surface here, which is not moving. So you can see I've labeled those pulleys A, B, and C, and the length down to where the guy is pulling it is called LD. And so we look at the equations for each rope, which are going to give us simultaneous equations. In this case, 2 ropes, 2 equations. So I won't go through this in a lot of detail, but for rope 1, here's how I can write that length. You can see that first length where the guy's pulling it down is going to be LD minus LA. And similarly for the other lengths of rope 1, again we go through and say that the change is equal to 0, and so we come up with one equation that relates 2 of these unknowns, delta LB and delta LD. Then we look at rope 2 in a similar fashion, and we come up with an expression for delta LC as a function of delta LB. Go back to the first equation, and we simplify that down to find that in this case the crate is going to rise at 1/4 of the speed that the rope is pulled. So next time we'll be looking at not dependent motion, but rather relative motion. And you see this if you're driving in a car and you look outside at the window at other vehicles, their velocities appear different. For example, if the vehicle is coming straight towards you, your 2 velocities add up, and it looks like the vehicle is coming towards you at that much higher rate of speed. So when you have a moving frame of reference, the apparent velocity of the other particle is called the relative velocity. So it's kind of a simple concept to do for these problems, but we'll find it really useful later on when you're looking at rigid body mechanisms. Then you work your way from point to point or joint to joint using this relative motion principle.